we've seen that in general there's no good way to define what the determinant of a linear map is, and that's because if you have a linear map from one vector space to another, to get a matrix representation, you have to choose a basis for your domain side, choose a basis for your codomain side. That gives you a representation, and then if you switch to different bases on the domain and codomain, that gives you a different representative, and those two are related by this equation. But there are so many choices built into this setup that the determinant after you make the change is usually going to be different than the determinant of the matrix before you make the change, right? The problem is you can really change the determinant quite a lot just by changing the basis on one side here, right? There's no sort of corresponding balancing change on the other side. But that sort of leads us to a special case where we do have some hope of defining what a determinant is, and that is the special case where we're going from one vector space to itself. And the reason that changes things is because, so if we change this setup so that we're going from V to itself, then we still have to choose a basis on the domain side, but we can insist that we use the same basis on the codomain side, right? And then if we switched to a new basis on the domain side, we'd have to switch to the new basis on the codomain side. So the changes that are happening on the domain side and the codomain side sort of stay in sync. There's a relationship between them, and this is what we were missing from the case where the codomain didn't have to be the same vector space as the domain. So in this setup, what would change here? Well, what's going to change here is, when we switch to the hats, so the representation relative to the hats is the representation, so D and D hat are being played by B and B hat, so B hat, representation of the identity on V, because our codomain space is V now, times the original representation relative to the original bases, but the original bases are both B, so rep BB of H, times rep B hat B of the identity on V. Okay, so, in here I'm missing representation of H. So now we can ask, what are the determinants here? So if we take the determinant of the representation of B hat of H, what we get is the determinant of all of this stuff multiplied together, but what we know about the determinant is that the determinant of a product of matrices is the product of the determinants of the matrices. So this is the determinant of rep B hat of the identity on V. So that determinant times the determinant of rep BB of our original map H times the determinant of rep B hat B of the identity on V. Okay, now things might look grim at first because, I mean, why should these... remember, what we're hoping is that the determinant of our original representing matrix, we're hoping that it will be equal to the representing matrix after we switch bases, because then we can call that determinant the determinant of the linear map. But it's not clear why these two things should be equal, because there's all this other stuff in the formula. But something we already know about these transition matrices comes to the rescue. So this transition matrix right here, rep BB hat, is the inverse of rep B hat B. That's something that we showed before, right? And then all the rest of this stays the same. Oh, I didn't write inverse matrix. Okay. But now that we know that this is an inverse matrix in here, well, the determinant of an inverse is the reciprocal of the determinant. So this is the reciprocal, or minus first power, of the determinant of the representation relative to B hat B of the identity on V times all the rest of this stuff, right? So I guess I really should write it out. Don't be lazy. So times the determinant of rep BB of H times the determinant of rep B hat B of the identity of V. But look, this times this, right? These products are products of real numbers, right? The determinant produces a real number. So we can rearrange this product, and in particular, we can get this part times this part, but those are reciprocals, so these parts cancel. And we're just left with the determinant of our new representing matrix is equal to the determinant of our old representing matrix. So this will let us make the definition that, I mean, why don't I just scroll down to it? This will let us make the definition that the determinant of the linear map is the determinant of any of its representing matrices. It will have many different representing matrices depending on the basis that you choose, but all of those matrices will have the same determinant. And that's really the surprising thing. If you're going from a vector space to itself, and you use the same basis on the domain and codomain side, it won't change what the determinant of the representing matrix is. Again, the representing matrix will change, the determinant of it will not change. So this makes this definition coherent, right? You can use any basis to get any representing matrix to figure out what the determinant of the linear map is. Just as an example, let's find the representing matrices for this linear map from R2 to R2 relative to these two bases. So relative to the standard basis, this is sort of the nice special case where we can just write down the coefficient matrix. So it's, oh, this is supposed to be an A here, otherwise it's not a linear map. So the coefficient matrix is just 1, 1, 5, 6. Okay. So to find the representing matrix relative to the basis B hat, we're going to actually write out this whole mess here. Right? Write out this. And remember that this one is the inverse of that one. Right? So we need to find one of the two transition matrices, either from this basis to that basis or vice versa. And it's easier to find the representing matrix from B hat to B. Okay, because B is the standard basis. So I'll write it down and then I'll justify why it's correct afterwards. So it turns out that if your standard basis is the second one, you just write down the basis vectors. So 5/3 minus 4/3. Okay, so you see I just took these two basis vectors in our new basis and just made a matrix out of them in order. They have to be in order. And that gives us this transition matrix. Oh, and this is representation of B hat to B of the identity on R2. Sorry, not F. Okay, so why does this work? Well, remember how you calculate this representing matrix is you take one of these basis vectors, this one, say, I'll only do the first one, you can do the second one yourself. You hit it with the linear map that we're representing, and we're representing the identity on R2, and then you find its representation relative to the old basis. Okay, so we want rep B of what is the identity applied to this vector? Well, it's the same vector. Right? The identity map is the one that doesn't change anything. And then relative to the standard basis, what is the representation of 1/3 minus 1/3? Well, it's 1/3 minus 1/3. So if the second basis is the standard basis, then you can, to get this transition matrix, you just take these vectors and make a matrix out of them. All right. Of course, now that we know the transition matrix from B hat to B, the representation, or the transition matrix from B to B hat is just the inverse of the transition matrix from B hat to B. So we'll take this one that we already calculated and then take its inverse. And I've calculated that ahead of time. I won't drag you through it. So it's minus 12, minus 15, 3, 3. Okay. Now we can write down the representing matrix relative to B hat of this map H. So it's going to be, have to get everything in the right order here. Which one do we want first? So this one goes on the left, then the old representation, then that one. Okay, got to get those in the right order. So minus 12, minus 15, 3, 3, times our old representing matrix, 1, 1, 5, 6, times the other transition matrix, 1/3, minus 1/3, 5/3, minus 4/3. And if we multiply all this out, which I'll let you do the arithmetic if you want, but what we get here is 5 minus 9 minus 1, 2. Okay, so great, we got this matrix. So remember what we're checking here, there are two things that we could check to see if this matrix is a plausible result. One thing we could check is we could take some basis vectors from B hat, multiply them by this matrix, and then see if they give us what it's supposed to give us. We've done that sort of thing before, so let's not do that. Instead, let's just compare the determinant of these two. Remember, the determinant of these two are supposed to be the same, because supposedly we figured out that the determinant of two matrices that represent the same linear map relative to different bases, those two determinants should be the same. So let's find the determinant of this one. This one's easier. 6 minus 5, so 1. Right, and now let's find the determinant of this one. Oh, actually, this one isn't too bad either. The determinant of this one, 10 minus 9, that's also 1. So these determinants really did come out to be the same. Of course, that's no surprise given what we know about all of this, stuff happening in the background, but it is nice to see that these determinants do come out to be the same thing. And it's this that lets us define the determinant of a linear map.